Okay, if everybody could take your seats, please. We'll get going here with the final event for the day. Obviously, flexibility has been the mantra all day, and I really want to thank Tom Irvine, who's the member from the American Institute of Aeronautics and Astronautics to my far left, who put this panel together and who we partnered with to bring this off. It was kind of touch and go all day, but Mark Cirangella from Sierra Nevada, right next to Tom's right, came all the way from Denver just for this. Now, I mean, he's obviously doing other things. Yeah, so he... And then Kyle Royster to my left from Mantech, who is our DARPA rep. And so I will get off the stage, turn it over to Tom. And again, thanks for coming out, especially at the end of the day with all the snow and everything. Really appreciate it. Tom?
Okay, thanks, Tom. Appreciate the introduction. And if you didn't hear Mark, who's from Denver, he said, this is not snow. I grew up in Cleveland. This is a dusting. But I do want to thank those of you, the hardy souls who are still with us at the end of sort of a brutal weather day here in Washington, D.C. So when Carl first contacted me, he said, we talked about putting together a panel where we talked about some space technology and specifically reusable both orbital and suborbital vehicles, and maybe more specifically, the propulsion system or the rocket motors or engines. And then with an eye toward potential future Navy applications or even future Navy programs. And so I thought, great, I'll reach out to people from what in the space industry we call new space, and Mark represents one of those companies, Sierra Nevada, probably one of the larger ones that we know as New Space. And I thought I'll reach out to DARPA because they're doing some pretty interesting projects along these lines. And the project manager is a fellow named Jess Sponable. And Jess said, "Yeah, I'd be happy. I'll reach out to some people. I'll moderate the panel." And so we put together about 5 people who were to show up, and then 2 weeks ago, Jess sent me one of those notes that you just hate to get if you're organizing something like this. Like DARPA moved a big program review right on top of this conference. I'll try to do my best to find substitutes, and in fact, he did that, and that's how we got Kyle. And we had another person from a company called Maston, which is also making reusable propulsion systems or rocket engines. And then the weather looked like it was going to be worse, and people had to be on the West Coast, and people had to be in Florida, and flights were canceled. And so we have 2 panelists and myself, the moderator. But I can tell you, both of them have really some interesting prepared remarks, and then we will get into some questions and answers. And again, we'll try to keep an eye on potential future Navy applications. And so, how I'd like to start is by having both Kyle and Mark describe what they're working on, either their organizations, the technologies, in the case of Mark, the products, with some specifics on the reusable rocket engine technology that we've been developing, testing, and in the case of Sierra Nevada actually flying. So my request to Kyle and to Mark was pretty non-specific in terms of observations about possible Navy applications, weapon system, propulsion system applications, things like that. So we're really counting on interaction with you after the prepared remarks to get a sense as to the type of technologies that we'll describe today, what the future may hold or what the future may be in terms of those naval applications. So with that, I'd like to start with Kyle Royster, who's here at the behest of Jeff Sponable, the DARPA project manager for the experimental space plane, or what's called XS-1. Kyle's a principal engineer at Mantech International Corporation. Mantech, probably most or all of you are familiar with Mantech, but they're a leading provider of innovative technologies and solutions for mission-critical national security programs for the intelligence community, for Department of Defense, for Homeland Security, and quite a few other government departments and agencies. Mr. Royster has a bachelor's degree in aerospace engineering from the University of Virginia and a master's degree in systems engineering also from UVA. So go Who's, right?
That's right, wahoo wah.
All right, Kyle.
Okay. Should I stand or?
You can sit or stand, whichever.
Okay. Well, I'm going to talk to you a little bit about this XS-1 program, experimental space plane, and the real goal for this system that we're developing at DARPA is to enable affordability to space through reusability. As you can see from this slide, it's just basically it summarizes a lot of the current systems we use for getting access to space and putting payloads there. And bottom line is we pay a whole lot of money to put different systems into space. We're losing our competitive advantage because our foreign competitors are also being able to fabricate these cheaper systems, and we actually import some of the technologies from the foreign contractors. Another problem we're looking at is being able to surge that launch capability. Currently, when we're trying to put stuff into space, it takes multiple years to be able to get anything there. And we run into delays due to either payloads or launch vehicles. So we want to be able to have a surge capability actually with XS-1 where we can do 10 launches in 10 days and actually want to demonstrate that. More about XS-1, basically what I was saying is we're trying to break that cycle where we have to put these expensive payloads into space that are very robust, that can stay up there for many, many years, and then they only need to be launched every so often. So that's sort of been the cycle as we've been launching. We'll build a very capable system, and that system's got to perform over a long lifetime, and that means you don't launch several systems. So we want to change that sort of vision by being able to replenish systems more as industry does. You have a new iPhone every year actually. We want to be able to just replace our satellite systems without having them be super robust, and we need to do that by enabling affordable launch. So the goal for XS-1 is really a reusable first stage. That's what we're after. So the way the payload gets to space is we have two stages. We have the reusable first stage and then an expendable second stage. We want to do the fly 10 times in 10 days and show the logistics to be able to do that and actually demonstrate it, and have some sort of payload that we get to put into orbit at the end of our program. And basically we want to do that for under $5 million for the whole vehicle. We recently awarded 3 different prime contractors on this effort. They're Boeing, Northrop Grumman, and Maston. They all came to us with very innovative proposals on how we could do that, very different systems, from sort of the vertical takeoff, flyback approach with the wing, and then being able to do the vertical takeoff and vertical landing recovery. We also have multiple small technology awards that we're really looking at enabling some of the more low risk or high risk technologies, such as the engines that you're talking about, thermal protection systems, different lightweight tanks to really get the propellant mass fraction down so you can get more payload into space. This is just a notional vehicle that we had put together leading up to it. You can see it's about F-15 sized for that first stage, and it's gotten a small expendable second stage on top of it. This vehicle in particular was designed to put about 3,000 pounds into orbit. You can sort of see it's got a goal of going up to Mach 10 before it launches that second stage. So not only does that enable getting a large payload to space, but it's also good for some of the hypersonic type testing that we've been trying to get into. It's really hard to do that affordably, so it gives you a reusable capability to enable some hypersonic test. This slide just shows our long history of space planes. You know, this isn't really something new. We've been working on it since the 1980s and before then even. So we've had a lot of programs, put a lot of money into it. And going forward, the thing that we want to do differently is, as this slide shows, we don't want to, a lot of the past efforts have taken a lot of high-risk technologies, tried to integrate them and then make the system work. Space shuttle, very high risk, low TRL technologies that we had to incorporate, and ASP and VentureStar are the same. So the way we want to break that cycle with XS1 is take a lot of the mature technologies that are already out there and be able to integrate them into the system. So the system design is a little bit complex, but we want to take very mature technologies to show that, you know, we can make this happen. We don't want to make, we don't believe in making the best system. It doesn't have to perform optimally. It's just really got to be functionable, reusable, and it's got to be maintained like an actual aircraft. This is what I was talking about breaking that sort of cost goal when it comes down to putting stuff into orbit. You can see the up arrow shows, you know, how we're putting lots and lots of more money into our actual payload systems. You know, getting a GPS system up into orbit used to be down in the $50 million range, and now it's getting up to the $300 to $5 million range to get that robustness where it can stay on station for many, many years. And what we want to do is break that curve by getting the access there so we don't have to have robust systems that stay up for a long, long time. So we save money both on launch and on our payloads. Like I was saying, not only does having a reusable first stage enable some of the things for getting payloads into space, but also a hypersonic testbed platform. It really opens up what we can do in that arena. So just in general, that's what we're doing for XS1. It's moving forward right now. We're finishing up our first phase this year. We're looking to fly probably in 2018, 2019 timeframe. We're going to be demoing that first stage with an expendable second stage. And hopefully when we really demonstrate that we can do this reusability, we get to a point where we can actually show that, you know, you can break that cost cycle and show that you can be repeatably able to put payloads into space. I guess I'll just elaborate a little bit on the ballistic missile defense role. That was more just a DARPA technology brief, but as far as getting into the ballistic missile world, you know, you talk about using reusable rocket engines, how you access space. I don't know if the Navy would go off and actually design a whole reusable system, but it would be good if they could leverage some of the investments that we're making. Somehow industry would make it, and maybe look into how they could use these reusable engines. I know some of the systems out there, SM-3 for Aegis and ballistic missile defense cost, you know, tens of millions of dollars just for one shot. So the engine, I'm sure, is a very expensive part. So we can really work that technology to bring those engine costs down. Hopefully the Navy and future systems would be able to utilize that. And that's just initial thoughts, but answer any questions if you have any, or we can move on to the next brief.
Yeah, Kyle, let's go ahead and have introduce Mark and let him give his briefing, and then we'll get into
Sure.
We'll get into questions. So we'll move to Mark Sarangelo, who is the corporate vice president for Sierra Nevada Corporation Space Systems. Sierra Nevada produces satellites, space transportation vehicles, propulsion systems, and space subsystems. Recently, Sierra Nevada was recognized as a best technology company to work for. It's a multi-billion-dollar business in U.S. aerospace and technology, employs over 2,800 people, and Mark, you're at least in half dozen states, if not more by now. It's become a fairly good-sized company. As the head of the space as the head of Space Systems, Mark has helped to build and grow a product portfolio ranging from small satellites to space technologies that have enabled over 420 planetary missions, such as Curiosity, to the hybrid rocket motors that won the Ansari X Prize. Sierra Nevada is also developing the Dream Chaser. It's an orbital space plane designed with multiple capabilities to transport crew and cargo to low Earth orbit. Mark was formerly chairman and CEO of a public traded company, Space Dev Incorporated, and that company merged with Sierra Nevada Corporation. He spent most of his professional life as an entrepreneur, where he's founded and led several successful technology and communication companies. He's the chairman emeritus of the Commercial Spaceflight Federation, a member of the Board of Governors of the Aerospace Industries Association, or AIA, and has been inducted as an Associate Fellow of the American Institute of Aeronautics and Astronautics. And he was named to Defense Industries Fast Track 50, Deloitte Fast Track 500, selected as a finalist in Ernst & Young's Entrepreneur of the Year, and has been included in Inc. magazine's top 200 companies, and was inducted into the NASA Space Foundation's Technology Hall of Fame. There's one other thing I want to mention about Mark, because I think most of you are probably either have a technical background or been involved in engineering or technology. For over 20 years, Mark's worked very passionately to make the world a safer place for children. He's a board member and trustee of the National Center for Missing and Exploited Children, and is a founder of the International Center for Children. The center has resolved over 100,000 missing children cases and created such nationally known programs as Amber Alert and Code Adam, which I'm sure you're all familiar with. In 2013, Mark was recognized for his efforts to promote innovation. The governor of Colorado appointed Mark as the chairman of the Colorado Innovation Network and as a chief innovation officer of the state of Colorado, which is a voluntary cabinet position, really unique in the country. I'm not sure any other state has a position quite like that. He's a member of the Chancellor's Advisory Board for the University of Colorado, and had a good discussion with Tony about that. And he's served the country proudly and with distinction as a U.S. Army officer, and I'm sure you guys won't hold that against him since you have about a 13-year winning streak on the football field. And
unfortunately on the basketball court this year.
He has a Bachelor of Science degree, an MBA degree, and a doctorate degree, and you didn't tell me where from, so.
I'm not going to say the Naval Academy. That's not going to work very well. Well, that's unfortunately the very long bio. Thank you for sitting through that. I'm happy to be here and just to give you some insight into what's going on in the space world. We're very fortunate to touch all the services as well as most of the civilian agencies. And if you can bear with me, I'll give you a little bit of an overview of our company and what we're doing. I'd like to start by saying we're not the beer company, unfortunately, for those of you who know Sierra Nevada. For the many years, as you've heard, we're employing about 3,000 people. Most of them come through my doors and want to know if there's a beer ration that goes along with their job. And the answer is no. But after years of hearing this, we've been around a lot longer than the beer company was. We finally called the CEO of the beer company up, and I said, maybe we should start talking because we're giving you an awful lot of promotion here. So the end result of that was actually pretty unique. Instead of fighting for this naming right, we actually joined together, and he said, why don't we make a beer together? And so I had the very hard distinction of going to my team saying I need 12 volunteers to go to beer camp for a weekend. You can imagine how hard that was going to do. And those 12 people actually went off and designed a new beer, and that was rolled out and is being rolled out. It's called the Mach 25 Ale. IPA. If any of you know beer, IPA is Indian Pale Ale, but we call it Intergalactic Planetary Ale because it's part of our business. And Mach 25 happens to be the speed of my spaceship, so that was always a fun thing to do. And it's being marketed as the smartest beer in the world because it was designed by rocket scientists. So. That's my opening introduction. You've heard a lot about the company in the opening flight. We've been around 26 years of space flight. This just did our 425th mission into space. We're launching something about every 3 weeks this year. And the beer story I tell in part because a lot of people don't really know our company. We're a pretty quiet company. We're privately owned. The people who own the company run it. We're fortunate enough not to have any debt or any outside investors, so we don't really need to go off and tout ourselves. We work pretty quietly amongst our clients and do pretty well with it. A significant part of what we do is military and classified work. But we're quite active. We have over 70 programs in space alone going on this year. And they span the spectrum of many different things. About 3,000 people currently operating in 26 countries and 1 million square feet of operations, and just to update you, 17 states actually. So throughout the United States. In space, we do four things. We're the country's largest builder of small satellites right now. Small satellites are, there's no specific term for what that means, but in visual, it's refrigerator, washing machine size, basically. We'll launch 11 of those this year of various types, mostly working in constellation. We are one of the country's largest builders of what we call space technologies. These are the enabling technologies that allow for large interplanetary missions to take place or geosatellites to take place. So if we were building a car on the small side, we'd build a small car. On the technology side, we'd be building the brakes or the transmissions for enabling those large missions to go on. And we do that for virtually all companies who do those larger missions, as well as for NASA and most international agencies. We're a propulsion company. We are not a launch company, unlike United Launch Alliance or SpaceX. We're a propulsion company. Equivalent of that in the aviation business, I'm a pilot since I was a little boy, is that we would be Pratt & Whitney or we would be General Electric or Rolls-Royce building an engine for an airframe. And we do that for ourselves, for satellites, and for other people. And then lastly, we're the owners and builders of a orbital space plane that's named Dream Chaser. And I'll talk a little bit about that. And what's I think most interesting is that most people see space as a derivative of airspace. Actually, the foundational engineering behind that is submarine-based. And not many people know that. I don't normally talk about it, but I figured this would be a good crowd to introduce that. And I'll tell you how that is derived. Last year, we passed 25 years of doing this, and I look back on our history, and we did this poster, which was sort of fun, and it's got out there. Is that we visited 7 planets with something that we've built. We're about to visit Pluto. For those of you who've been following that, it's a mission called New Horizons. And New Horizons was launched 10 years ago. It was actually designed and green-lighted 18 years ago. And it takes 10 years to go from Earth to Pluto, going 20,000 miles an hour. So you can imagine the distances there. It's about a 4.5-hour communication, a one-way communication loop. So it's a long way, and we're about a week or two approaching the first real good visuals. We've got our first visuals. So after 10 years of working through all the stuff that can happen in space, all the bad stuff, the little planetary mission is going to get there. And the only sad thing is that somewhere in about the 5-year time frame, we had the phone call the mission and say, sorry, you're not a planetary mission anymore. Somebody decided Pluto wasn't a planet. It was a really pretty hard call. The little guy was crying for the next 1,000,000 miles. It was tough. It was tough. But it is going to get there. In a few weeks, you'll remember this talk because you'll start seeing some amazing pictures from the planet. And by the second week of June, we will do our closest pass ever to Pluto. On the other end, many of you deal with really difficult technologies. We were just made part of the mission that's going to go the closest to the sun that there ever has been. It's a mission that will be about 4.5 million miles away from the core of the sun's surface. And you can imagine the heat and the radiation and all the very, very tough conditions that we'd have to operate under there. The idea for that particular mission is to be able to understand the solar weather, solar storms, solar tsunamis, as we like to call them, which are very, very disruptive for our technology in space. But to engineer that type of mission going from as far away as you can go and as cold as you can go in our solar system to as hot as you can go, that's sort of the span of what we do. We do many types of things, and what you see in this last picture, many of the new satellites as we go forward are not actually launched as individual satellites, although some of what DARPA is doing is one at a time. But what we currently are doing is collectivizing these satellites. What you see here is 8 satellites that are about 250 kilograms apiece. They were launched, this is an image, but we actually did launch this particular set last summer. And the 8 were launched off of, it could be of a EELV, an expendable launch vehicle, or a Falcon launch system, or a Ariane launch system. But you put 8, anywhere from 8 to 12 within a launch cone of the launch system, and they're able to deploy them that way. And that's something that's working fairly well. We've had the opportunity to do some pretty interesting things. We helped build 2 of the explorers that were on Mars, Spirit and Opportunity. That mission was given a 3 to 6 month mission life. It's now over 10 years, and one is still operational. And you can imagine that as a contractor and a builder and engineer and technologist, I get a phone call from my government client to be held nameless right now every few months. And it's been a long time since we've been doing this, and he picks up the phone, he doesn't even say hello, he starts cursing me. Very loudly, usually. So I put it on speakerphone for about 5 minutes, and he calms down. And we were on time, on budget, and we lasted 20 times longer than the operational life. You would think that would be reason to be happy, right? Most of you would be. The problem is that the person on this particular other end of the phone call can't get off this mission until these things die. So every few months he calls me and he says, I'm having these nightmares of rover suicide where I take the joystick and I just push it forward and drive the damn thing off the cliff so I can go on to the next project. It's an unusual phone call from a happy client, let's say. We do a lot of interesting deployable systems which actually do have Navy work. And of our base of people who've come out of the military, about 25, somewhere between 25 and 30% of those have a Navy background. So it's an interesting collection. You wouldn't necessarily associate that way, but a lot of what we do these days is weather-based, particularly in the satellite area. So there's a lot of work being done there. We've done a number of different interesting missions. Probably most famously recently was the Mars Science Lab. If any of you saw 2.5 years ago, 2 years ago when we landed on Mars with a rover called Curiosity. There were 7 minutes of terror. Some of you might have seen that landing. It was viewed by about 400 million people. That was an interesting background to that particular story because we had we had many things, but the one thing we were doing was we did the landing, the last minute of the landing, basically the lowering of the vehicle to the surface. And when you realize that this was a very large, multi-billion-dollar mission, it takes 9 months to get to Mars, all this work, we all went off as a team off to Pasadena to watch the landing and sort of as a collective, hey, we're going to win or die together. And we got there and some person from NASA came through the door and said, great news. We're going to have our satellites in a right exact position. We're going to be able to see each part of the landing and potentially photograph it. And we're all, wow, that's great. We've never had this before. Then we all realized that means that of the 30-some-odd steps, we're going to know who screwed up. And then I realized that I'm the last part of the program, the little last thing to happen. So if there was 28 other happy people around the room, I was going to be the thing, or my company was going to be the thing between success and failure, and in doing it in front of 400 million people live. So it was always an interesting world. I ran out of Valium that day, but I won't go through a lot of this, but suffice it to say, we do quite a lot. What you see in this particular picture, for those of you who haven't seen, are examples of what we call small satellites. And the interesting thing here is that from the last 5 to 10 years, the capabilities of these satellites have grown enormously. And I'm not going to go into too much detail, but basically 10 times the capability than we had just 5 years ago, and a whole lot less cost. We're actually building on an assembly line these satellites now, which has driven the time to build from 2 years down to about 4 months. It's dropped the cost by about half, and the capabilities are going up by anywhere from 5 to 10 times in terms of communication throughput or optical quality. It's really been a significant game changer for what we try to do, including recently we won the nationally competed competition. We were the only winner to create the next generation of satellite. This was an Air Force competition, but it would be then put into the government catalog to be able to be used by any of the services. The creation of a very essentially plug-and-play, simple, direct satellite that can do a number of small things in low Earth orbit. On the engine side, we are one of our companies is called Orbitech, and they are developing and testing right now the next generation of motor systems. And what's particularly interesting about this is that the same motor system, there's two main goals for this, or three main goals. It's reusable, it has the ability to scale significant by multiples, and as you see on this picture, for those of you who have any background in propellants, it has the ability to use multiple kinds of propellants in the same motor system without changing out the whole system. In effect, if that was my car, that means I could run it on electricity, I can run it on diesel, I can run it on ethanol, I can run it on gasoline, and use the same engine to do that. That has not yet been done in the industry, and it's not theory. We are now doing ground-based test fires on this. We have, in total, done about 100 or so motors in our career. and have, as you heard in the introduction, have won a various number of prizes, including being able to be the first company to take a motor and be reusable at a significant size and Mach level. So we have a significant amount of experience. This gives you a sense of the look of the motor system, and it can go basically by varying the number of thrust chambers and the number of pieces of the motor, we can create much larger motors using the same basic system. This part of our business, we also do what we call ECLIS. ECLIS is environmental control, life support, and thermal systems. Basically, when you're in space, you have a self-contained system, much like you do on a submarine, and you have to be able to do that. And a lot of this technology that we're developing for space-based, long-distance space travel or long-duration space travel is being ported over to make undersea activities and controlled activities in the military. And finally, in this particular area, we do a little bit of an anomaly. We're an advanced fire suppression system company. And basically, the technology, without going into today, it can extinguish fires in about half the time with about 1/3 of the water. And that technology is being deployed throughout the first responders and is being tested and looked at by the Navy. Finally, to give you a little bit of talk of our vehicle, the Dream Chaser, if we could run the video, you'll see a glimpse of the next generation of piloted and autonomous low Earth orbit space system. The system itself has been developed now over 10 years. It was originally a NASA vehicle. It's in flight test now, so it's not a theoretical system. It would be launched, in this case, on an Atlas V, but it has multiple launch opportunities. And it is a completely reusable system, expected to get somewhere between 25 and 30 flights in its human version and probably around 15 or so flights in its autonomous version. And the vehicle is designed to be able to land on any runway, any commercial runway, basically a 737 class runway. It has no hazardous materials on board. We designed out all hypervols, all hazardous materials, so literally we can and would be able to land at any commercial airport. It takes, it's about 8,000 to 9,000 foot runway, approach speed is 190 knots, for those of you who know anything about aviation. And it carries 7 people to space, and very much, we call it our space utility vehicle, and very much like a space utility vehicle, it can take the seats out, and you can take all cargo. It's fully autonomous, not ground controlled, but fully autonomous. Its first flight actually was an autonomous flight. So it is what we call optionally piloted, or OPV, which means that inherent in the same architecture is both the ability to fly autonomously or fly piloted. And we can alternate between the two architectures using the same system. I won't go too much into it because time is getting short, but we basically have 3 missions for this particular vehicle. One is what we call working in space, short duration missions, going back and forth to the space station, or fixing things in space. Satellite servicing is a big aspect, and in fact, the Navy particularly is relying on a number of weather satellites and communication satellites that are coming to the end of life. We can do long duration missions or extended duration missions, human run for a month or so in the same vehicle, or a long duration mission uncrewed for a year or more, all using the same basic system. And for those of you who don't know, the space station pictured here is now been classified as a national laboratory. So it is accessible to anybody doing research, and the types of research being done on it that are quite significant: muscle atrophy. When you go into space, you begin losing your muscle tone within hours, and within 6 months you lose about 10% of your bone mass and a lot of your muscle tone. Same types of things that multiple sclerosis patients have, or long-duration hospital patients. Certain diseases speed up or slow down in space, and we're able to identify that, and if we can do that, and sometimes you want to accelerate a vaccine or slow down a disease. Your eyes are one of the first things to go in space as well, because your eyes are fluid and there's no gravity. So you begin to see visual impairment, which is very similar to a number of eye diseases that are earthbound. And probably most exciting to me, there's been a lot of study being started for Alzheimer's. We found out that Alzheimer's actually slows down in space. And so when you look at all these, what we're trying to then do is to say, in addition to being able to be reusable and to do all the things that NASA may need to do or fix satellites, that eventually what we want to be able to do is have self-contained laboratories using the same vehicle. What you see here is a cutaway of 1/4 of one size of the vehicle to give you a perspective, and it has about a 10 or so scientific missions in it. The big difference between us and the space station is the space station is a fixed laboratory. We are able to fly up with a set of experiments, stay up for a month to a year, and then fly that whole mission back home to a runway instead of splashing it down in the ocean. And that creates the opportunity to do a variety of research in space. It also creates the opportunity to have what's now being called in the military force reconstitution. If something goes wrong with our satellites or with our optical systems, we can actually put replacement of those into this vehicle and be able to fly this vehicle for those purposes. And to just finalize this and talk a little bit about some of the practicality. What you see here is one of my favorite pictures. This is one of the first high-def pictures from Mars, and it shows you the drill bit that's being used on the Curiosity rover that's up there now. Curiosity is actually nuclear-powered, for those of you who don't know, not solar-powered. And this particular drill bit has to have the ability to drill into many different kinds of surfaces. And you'll see it looks like a rotating at the end. I don't know if I have a... Oops.
There is a laser there, yeah.
On this end, on the end here is a rotating drill bit that actually has 6 different implements to it. What's really fascinating, the reason I tell this, is out of this same arm, you're talking about being able to do something as pick up a pin 340 million miles away to drill into the hardest material. And the whole purpose of this is to have active science going on. But to make something like this, the technology that goes into it has now moved into prosthetics. It has moved into optical sensors. It's moved into new drilling technologies for the drilling industry. It's moved into alloys because we used a certain type of new alloy to build this. And a variety of things that make space special, including, probably most interesting, the movement into prosthetics, active neurological prosthetics, to be able to move using your brain instead of moving using mechanical means. And that's why we believe the space industry is quite good. And I'll end up with my Navy story. The Dream Chaser is actually a submarine in that it's a pressure vessel inside an outer skin. And that pressure vessel, which you see built here, is made out of the most advanced composites that you can find right now. So we are a composite test bed. Our composites have to deal with 25 Mach, as I mentioned, which is 17,000 miles an hour. It has to deal with extreme cold, extreme heat, unlike what you can see anywhere on Earth except at the lowest depths of the ocean. It has to deal with pressures that you don't see on Earth. So we're pioneering composite in a very different way. But the inside of the vehicle, which you see the 2 halves in the yellow here, are actually a pressure vessel, and then there's an outer skin. And the design cues here actually came from submarine work. And the ability to then to redo the inside of the pressure vessel to turn it into a flight vehicle or to take everything out and turn it into a cargo vehicle allows us to do that without doing any of the flight controls or any of the mechanical activities, very much like a submarine would be doing. So on that note, I'll just end that right now, with the exception of the one military program called X-37 program, we are the only vehicle that's actually a piloted space plane that's out there that's able to do all this work. And from that point, thank you.
Good, thank you, Mark. So what I mean, we're really here to interact with you and answer any questions that you have, and I know there's some microphones set up if you do have any questions. I'll go ahead and start, and I'll go back to Kyle. First of all, I should say, even though the session was centered around reusable technologies, either vehicle or propulsion systems, it is an opportunity to ask any question that you might have come to your mind during the presentations, either about the DARPA program or a lot of other work that Sierra Nevada is doing, which Mark just described. And so I'm sure either one of them would be happy to field whatever question you might have. So I'll start with Kyle. The XS-1 envisions a reusable first stage. It would fly at hypersonic speed at suborbital altitude, and then at some point, one or more expendable upper stages separate from that first stage and deploy either a satellite or satellites into low Earth orbit. And it seems as if the economic viability of the entire system's based upon that reusable first stage that would return to Earth, land, and then be prepped for the next flight. And there's a lot of, you mentioned that one of the keys to making or to ultimately being successful on this particular project are to use mature technologies in a lot of different areas, whether that's thermal protection systems or automated systems having to do with launch, flight, and recovery systems. And so I'm kind of curious, is there even though that's the philosophy, are there is there a significant technical challenge or maybe a few significant technical challenges that I think we sort of affectionately know as either high hurdles or long poles that really have to be overcome to make this XS1 successful? Or is it simply a matter of making the system of systems work as you envision or intend?
I think there is definitely a lot that goes into it. It's not an easy challenge just integrating the system. I mean, a lot of the stuff, there are still some immature technologies. When you get into the reusable world, that engine, we don't really have a reusable engine now that we use. You mean, especially when we're talking liquid engines and solid engines. It takes a lot to get that engine to be able to be cycled and operate more than one time. So all the stuff that goes into engines and having mature cycles that engine runs are very difficult technologies that we're having to overcome. There's some companies out there working it. SpaceX is working an engine. I think you see Blue Origin has some engines out there. But we're trying to either leverage what they're doing or have our own investments go into building that engine and making it be reusable over multiple flights. So we had that 10 flights in 10 days sort of goal, so that's at least 10 reuses of that engine. Thermal is always difficult when you're flying at Mach 10. You got to deal with all those thermal environments. And then as far as getting to that goal of being able to do those 10 flights in 10 days, imagine having to recover the system and then make sure it's certified to launch again within 24 hours. That's not an easy challenge to do and something we're trying to take on. There's been some programs in the past that have looked at that. I think DCX one had a goal to do some quick turnaround launches, but going for that, you have to recover the vehicle there. Then there's different ways to do it. Some performers are looking at flying Mach 10, landing downrange, and then having to bring the vehicle back to the launch site. So you've got to do all that, and then get it all set up, make sure the system's still healthy, make sure your thermal protection is still intact, make sure your engines are good to run, and then get it up and launch it again. So some performers are looking, I don't know if anyone's seen the recent SpaceX video where they were trying to land on the barge to recover it and didn't have so much luck. So some of the vehicles we've been looking at are that sort of vertical takeoff, vertical landing, and being able to recover it. So not easy just from a logistics standpoint, but also from getting to that Mach 10 type flight is very difficult as well. But we are trying to use more mature technologies to get there to make the problem a little bit easier.
Yeah, thanks. So some significant technical challenges, but also that system of systems does have to work and all hold together. You mentioned, I know there's a question here, but let me just follow up while this is on my mind, and I'll switch to Mark because his company actually has experience in this area. So, Kyle, one of the things that you talked about was the reusable engine and the challenge and difficulty of quick turnaround. Mark, your company actually has some experience with that because you did build the engine for Spaceship One, teaming with what's now Virgin Galactic, but at the time was Scaled Composites, and actually provided the propulsion system for that. So I thought it would be interesting if you could describe maybe a typical or perhaps even atypical, if it's appropriate and interesting, turnaround that's required from landing to the next launch for a reusable launch system and for the propulsion system. So what are all the considerations in doing that turnaround from technical to safety to logistics and other things that may be important?
Sure, I'll be happy to. Basically, you break it into two areas. One is a reusable motor system, and the other is a reusable launch system, and they're quite different activities. We're on the motor side of it, and the way we approached the problem was to effectively have a very hardened motor system with a with a cartridge system for the propellant. So effectively, it's like a razor blade theory. The razor blade, in our case, the motor system, was encased in a very significant motor system that had the ability to last 20, 30, 40 flights, but the actual cartridge motor system burned in, burned out, and was removed, and effectively then was replaced with a new cartridge. And much of the engineering that we've had, and we use this system currently, and it's had significant flight experience, including with humans on board. That system, the engineering went into doing exactly this problem. Instead of trying to work on the technology of the motor itself, it was how do we make it reusable, and then working backwards from that. The problem once you do that is then how do you scale it, because there's a certain amount of weight that's necessary to ensure that reusability, and you need, in the Spaceship One now 10 years, or just about 10 years ago, that was about a 20,000 pound thrust motor. We're now doing 60,000 pound thrust motors for the same type of operation. And that scaling, which is threefold, does not sound like a big deal in motor systems, but it is a big deal when you're trying to then scale for the reusability part of it. In our case, we spent all that time saying, let's do it in parts, one part that basically stays in and is able to withstand this kind of pressure for a long time, and the other part which is removable and consumable, that then gets replaced.
Yep, good, thanks. So a couple of you have been waiting patiently to ask questions. I believe the gentleman on my right.
Sean Walsh. I was wondering, I was thinking you were talking about these, this is the gentleman for Sierra Nevada, about the long duration missions, and these very, very reliable systems. And I was thinking, gee, you know, we've been talking about reducing affordability, reducing manning on ships for a couple of years, and one of the issues is always the preventive maintenance, and we're having to put people back on because they want to do the maintenance. But I'm thinking, okay, is there a secret, you know, are there lessons we can learn? Do you have a secret sauce for designing, you know, these systems? You know, obviously you have a harsh environment, ours is, we do too, it's seawater, which is somewhat different. But, you know, I'm just wondering if there's lessons that we could learn from what you guys do, that maybe design systems and affordable ones. You know, it sounds like you're also developing pretty affordable systems.
Well, we're trying, and I actually, that's one of the reasons I took this as a speaking, because I actually believe the connection between space and NAVC is quite significant, particularly in things even like suits. We're designing our own new spacesuit. It has a lot of cues from deep underwater suits, and there's a lot of connection between the two of them. But to get to your point, the hardest challenge we have is to then figure out how do we, because in space, particularly if it's autonomous, there's no service calls. You can't send somebody to go fix that even if you wanted to. And if we go long distance missions, such as to Mars or Pluto, 10 years of operations in an environment where you can't do anything except software, if you're lucky, and that's even difficult because of the time distances. So I think what we do is we spend a lot of time looking at what are mission critical, going to end the mission types of things, and then we essentially tier out the types of activities we're doing within the spaceship to realize that there may be 10 or 15 things we can do with a mission, and any one of those may be important, but the most important is being able to enable some of those to continue. So we, again, sort of this mindset of splitting the infrastructure that manages the activities going on from the activities themselves. The activities, as you saw in that brief picture, are basically plug-and-play types of laboratory boxes that allow for the work to be done inside an infrastructure on the outside. So we went into using materials like composites because composites have a longer duration life, at least in our environments. We dealt with how do we let heat out, because in a spaceship I'll travel around the Earth every 90 minutes. So we'll get 45 minutes of extreme cold and 45 minutes of extreme heat. And that's bad enough, but you're doing that in 90-minute cycles, so the compression and expansion of the materials has to happen in a very short period of time. So we spent a lot of time looking at protecting what's on the inside. And it's a very long answer, but I think the shortest answer I can give is to separate the life support, if you can look at it that way, the life support of the vehicle from the actual scientific missions and to put the energy into making sure the life support systems, the vehicle itself, redundancy in communication, redundancy in the ability to self-heal, that happens first, and then you can figure out how much weight you can carry in terms of the types of missions that we do.
Rick, before I get to you, Kyle, I'll put you on the spot a little bit, and you can decline if necessary. I mean, DARPA also does a lot of activity where they're concerned with long duration, whether it's air, space, or probably for that matter, naval operations. And I just, before I moved on, I just wanted to see if you had any thoughts on that same question.
Yeah, DARPA does look at those long-duration kind of missions. That we're actually trying to break out of that cycle a little bit, and I don't want to speak for the agency, so don't take my words as DARPA policy. But you know, we are trying to, from what I've seen, we've been trying to get to the point where we don't have to have the most reliable system. We don't deal with systems that go into space necessarily and have to be flying 10 years. We want to be able to easily and quickly replace systems by using mature technologies and be able to do sort of line item replacements as you need to, and don't stress, you know, having the best of the best system. We want to say, you know, let's take what's good enough, let's be able to make it affordable enough where we can just replenish it like you do in the commercial industry. You know, you get a new computer every couple of years, you get a new phone every year. We want to try to take on that sort of model of when it comes to building systems where you don't need to be the best of the best all the time.
Yeah, and maybe if we get a chance, we can circle back to what I think is a sister program of XS1 called ALASA, which I think has a lot of those type of goals. Anyway, Rick, you've been waiting very patiently.
Thank you, and gentlemen, thanks for your time on a snowy day. One of the growing concerns in every program, whether it's industry or government or anybody that owns a processor or a data link, is cyber. And I wonder if you would take a few minutes and talk a little bit about how you are hardening your systems so that you can guarantee the data link for a communication to Pluto or real life in a low Earth orbit.
Sure, we can certainly try. And it's an interesting example because when that Pluto mission left 11 years ago, the world of cyber didn't exist as we know it today. And some of you are involved in GPS and other certain systems. You realize that the biggest misnomer of my industry in space is that we're actually advanced. In some ways we're not, because by the time something gets built and makes it to the launch pad and gets launched, it's outdated. And it would scare you to know the computing power of many of the things that we rely on every day. But the answer is, I think, in the ability where we've spent a lot of our money is the ability to upgrade and rewrite the software. That is not something that has been in most of the historical spacecrafts. You can upload an entire new system, but the ability to do it in packets or in small segments and the ability to actually upgrade from the ground the complete software systems that manage the spaceships that we're doing in an encrypted, fast way is where we're spending our time. It is not possible, and at least in my view, to be able to design the onboard systems to be able to do that. So I think the defense is in rapidity, in the ability to change at different intervals, access points, and the ability to change the addressing of how the communication systems work. And that's where the money is going into, more than anything. What we've also found, to the other gentleman's question, is that a lot of my industry has spent a lot of time looking at redundancy and spending time to make things quadruple or even more redundant. And that drives cost and weight and exposure up through the roof. What we've actually found these days is the ability to, instead of having quadruple redundancy, have two of the same processors that are dual redundant. And it's cheaper, faster, and actually provides you more of a backup. And in terms of cyber, it allows you actually to do some interesting switching back and forth in intervals. And for a lot of reasons, I can't go much more than that. But I think that's where it's really going, is instead of trying to fight it with a big wall, we try to fight it by moving the wall around a lot.
Yeah, I guess I'll just throw out a couple points. I can't go into too much detail, but you know, when we look at sort of the cyber effects on our military systems, at least from the DARPA standpoint, You have those encryption devices on each end, so hopefully you have very good encryption that keeps people from getting in on your links. The other thing that we've sort of been throwing around recently is these heterogeneous versus homogeneous systems. So no two systems from a software or computing standpoint look alike. So if you can get into one, you can't get into all of them. So make them different enough so if they do get into one, not each of those systems has that same vulnerability. So those are just some of the things we've been looking at.
Okay, Tony, you had a question?
Yeah, I do. First off, thanks for being here on the day when we're not too many. Mark, maybe two thoughts if you might offer them to us, and then I've got something maybe Kyle can address. I noticed on your slides, Mark, the docking station technologies and the remote sensing part.
Yes.
The last I heard from the Navy in terms of deep submergence and remote vehicles operating autonomously undersea was the docking capture problem, the ability to do that autonomously with surety. And maybe there's some lessons there that you might be able to pass on to us, or thoughts about how to get connected, and maybe you're already connected in that one. And the second one, I happened to be in a lecture that Dr. Ballard was giving about basically an avatar, the remote sensing, the ability to extend your senses millions of miles, or in his case, deep below the ocean, to where you're actually feel you're connected to the environment around you. And so the question on there is, how far are we away from the ability to dial a person up on the phone, put them in the sense, and actually touch rocks on Mars and have them do the tactile side of it?
Yeah.
And Kyle, to think about it, if there's any thoughts on the propulsion side, thinking about the reinvigoration of the triad, either the anti-ballistic missile defense, missile propulsion, or the as we look to refresh Minuteman and so on, the connections there. Sure.
Very good. The first question on the docking, it is another example of how space and underwater Navy are inherently connected. For a lot of very obvious reasons, when we do a dock in space, it has to be a complete seal dock. Even the smallest of problems will result in a destroyed and probably catastrophically injured crew. So we spend a lot of energy spending time on that. It is probably no different than a rescue submarine, for example, that has to be able to dock with another submarine underneath to take a injured crew off. And I think from that technology point of view, we are actually looking to partner with an explorer, because there's a lot of NRE going into figuring out the next wave of docking systems. And in my view, that's stuff that should be available through the military as well. And we're encouraging it, we're open to it. We think it makes a lot of sense for that to happen. On the Avatar, that's a fascinating question. We actually have an Avatar system that does our design work right now. And so I didn't show it today. It wasn't something I actually thought about, and maybe I should have. But had I did, you would have shown a video that basically has a complete interior designed Avatar system for the inside of our spaceship. And you would be able, we are using it right now to figure out how we load a spaceship, and how does an astronaut move things around, how do they operate, how do they control the flight deck. And that's done through a system that has some level of tactile feel to it, interestingly enough. It's not yet projectable to the type of level that you're talking about. The Mars issue is mainly one of communication. It's an 8 to 9 minute communication path one way to Mars from the Earth at this point in time. So that's where you run into the problems. But within the design world, in some ways, the low Earth orbit, 100 to 200 mile orbit, we think we can get there, and we're actually using it right now. So we're not that far away from perhaps doing something that's even a little bit further. Interesting enough, probably the fascinating connection to that is remote medicine, which is where we're partnering to talk about how do we take this system that we're building and be able to project it to someone being able to assist in an operation from a long distance. Maybe not as the primary surgeon or doctor, but someone that might be a support person, using a robotic support to a secondary physician who may not have the skill sets.
I'll hit on that ballistic missile defense type question. I guess when it comes to the XS1 program and what we can contribute to that as far as refreshing technologies that go into there, what we're really looking to do for XS1 is sort of mature the technologies enough where industry wants to play more, and they want to invest their money to build these systems, get some competition going to reduce the cost of space access. So when it comes time to refresh those sort of systems, we'd be able to pull from industry to go out and compete some new propulsion technologies to allow that price to come down. We're really geared to affordability, not necessarily capability when it comes to ballistic missiles and ballistic missile defense. So hopefully, in the 5 to 10 year time frame that we're looking at to start investing technologies and have industry go forward, we'll be able to look even further down the road to see how we can upgrade those sort of systems.
Hi, Rick Hepburn. As you know, the Navy's very interested for their ships and submarines for survivability is a big thing. So for space vehicles, how does survivability enter the picture? You talk about cyber survivability. I noticed you had a fire suppression system, but if things are detonated in orbit and you run into it, or you got an EMP pulse you run through, can you talk to survivability of your craft?
Yes, breach of our hull is fairly catastrophic, so we spend a lot of time on it. One of the reasons for the move to composite is that exact survivability. What we've found is that, I don't know how much you know about composites, but composites essentially, you layer composites to get strength. And in that layering system, if you crosshatch it the proper way, you actually create some level of barrier to penetration. And then if you insert, depending on the type of skin that you're talking about, essentially brakes that allow it to, if it hits something, it'll stop for a moment and have the chance to self-heal, because certain types of composites that we're using have some self-healing capability if they're given enough time to do that. So a lot of the energy is put into that. Our survivability goes beyond the physical, though. We have to, the biggest issue most people don't realize of going to Mars, for humans, for example, is really not the time. Everybody talks about how long. It's a 9-month journey. People have survived 9 months. Some of you may have been some mariners, have been underwater for 6 months or longer. That's not really the issue. The issue right now is radiation, for the most part. How to protect the crew from 9 months of direct sun radiation with no protection, and the amount of systems that you would need to keep that out for that length of time are so heavy that we can't possibly go there. And someday we'll go there faster, we'll have better motors, better systems, but we're still going to have the problem of being able to maintain. A human cannot last in that type of radiation environment for long. So similarly, what we're trying to do is figure out how do we create environments that protect, put barriers, in a sense, put multiple types of barriers in the same outer skin and inner skin. And what we're finding actually is putting different barriers is something that's interesting as well, making them, some of it is organic material, interestingly enough, that growing the food, for example, on a long-distance journey, doing that inside the walls of the spaceship actually is an absorption to the radiation and some of the issues on the outside. So I know that's not exactly your question, but I think the answer is in having systems that are somewhat self-healing, have levels of essentially wall protection that allow for some time for things to be shut off. Similarly to submarines, we do have the ability to compartmentalize, but it's not great. So we can airlock, for example, certain parts of the spaceship and move to another part. So you can harden the crew capsule, the crew area in the front of the spaceship, where we have an airlock in the back, you might put less material. So that's how we're looking at it.
For XS1, with the survivability standpoint, I think we acknowledge that space is vulnerable. So what we're trying to do is get industry to rethink how we do space, and that's why we're going after that, be able to sort of get to a rapid response to space, so we can do those quick turnaround cycles where you do, if we lose assets, we can replenish them very quickly based on our 10 launches in 10 days. We don't have to do that whole lead up to get a new payload in orbit. We have them ready to go, and then when the time comes that we need them, we can replenish them quickly.
Yeah. The biggest single threat to our normal existence right now is space debris. The projectile speed is 17,000 miles, and you don't need to have anything but kinetic energy. Any small piece of that, as many of you know from your own military work, would be devastating. That's combined with the fact that in my industry, weight is everything, because it costs so much to get things to space. So you're not putting armor on satellites, you're not doing things to protect them from this. And what's happening is the number of debris fields are growing, the satellites are not protected, and just last week we lost a satellite that self-imploded and turned into 47 or 48 pieces that are now flying around, any one of which could take out a major satellite instantaneously. So part of that is that we're trying, one of the reasons for our spaceship is we're trying to go up there and get rid of satellites that are no longer active, because that moves, it doesn't stop the debris that's there, but sort of like making our world a little cleaner, you have to stop somewhere, and one of the ways is to stop polluting. If you can push these satellites out of the way and get them to burn up before they destroy, like the one that just imploded a couple weeks ago, then you can help do that. But that's actually the biggest issue in terms of protection right now, and it's a big problem for us, for all of us.
And Kyle, to go back to something that you said, you mentioned the 10 times in 10 days key requirement, but for XS1, there's also the requirement to fly Mach 10, and that's a pretty significant environment in terms of, at some point, aero loading and aerothermal loading. Sure. And I wondered if that was a consideration in terms of vehicle survivability and how that's being addressed.
I mean, I was thinking of the survivability from a threat standpoint and,
Right.
what you'd face there. But yeah, certainly facing those kinds of environments just in thermal makes something you have to deal with and survive in order to get to that 10 times in 10 days. So yeah, being able to deal with those environments and then be able to either easily replace or fix what breaks in those environments so you can do that next launch, or just be able to deal with it and, like I said, be able to go again. So yeah, those are all things that we're dealing with for our XS1 program.
Right. Question here.
Good afternoon, gentlemen. I'm Kerry Filling with NAVC. I may have missed this early on in your brief because I'm dealing with ASNE logistics here, obviously. My question for you is a little bit about the social engineering, and sometimes we find that social engineering is harder than the actual engineering in our field, and I'm sure you do as well. And we in the Navy tend to keep our heads down and worrying about our problems, and we only get our news in sound bites and WTOP, our local FM news station. And so we hear things on the news on the way home like, SpaceX using Russian rocket engines blows up at Wallops Island. And I guess for some of us, that paradigm shift of, seeing the shuttle program, knowing that NASA was at the top of that, and of course we all know, being in the defense industry, that there's many contractors involved to support any major, entity. I guess I'd like to hear your thoughts on how you feel the management of that privatization of space is going. To me, it's surprising to see DARPA as part of that, and maybe I shouldn't be. So just want to get your thoughts on how well you think that's being managed at the federal level, and the interesting use of private companies launching things from public assets and things like that. So I'd just like to get your thoughts on how you feel that's going. Is it well integrated? Is it still kind of a Wild West frontier? Thanks.
So Mark and Kyle, before you answer that, I do want to just clarify something. So as a representative of AIAA, and both SpaceX and Orbital are corporate members, it was Orbital who had the accident at Wallops and not SpaceX. I just need to clarify that.
I was going to do that, but yes. But I think the question is actually a great question. One of the things another slide I sometimes put up, but I didn't, but we went back and looked at all the rocket failures since 1950, and there have been somewhere around 6,000 launches from globally. What was most interesting is that the rate of failure has not changed in the last 30 years. And despite what we hear, the rate of our communication level and the openness of the communication has changed dramatically. So we are actually getting instantaneous views of the rockets that are blowing up on Wallops and other places. But the truth of the matter is that the success rate statistically has not changed at all. Point one. Point two is that everything in the space, every space vehicle that's ever been built has been built by a contractor, at least from the NASA side. And I know the military has some work on its own, but the shuttle was built by a team of contractors, as it was everything else. The program management was government-based, and in this case, what the government is doing is buying a service instead of buying the vehicle. And that's really the biggest change that's gone on. It's really not the build of the vehicle that has changed all that much, to be honest. So I think that's the second point. I think the third point is that there's a positive movement to understanding that there needs to be some level of public-private partnership on these things. And that's what we do. We, in our case with NASA, we've invested virtually dollar for dollar with NASA. NASA gets a program that's a lot less expensive. We get NASA help and support, and we invest our own money. We keep the intellectual property in the vehicle, and that's our payoff for at the end of the day. And it's a rationalization to be able to do that. However, that's not new. It's been done. There's a lot of public-private partnerships in the utilities industry and many other industries. It's just never really been applied to space in this particular way. But then it becomes a costing issue. And just a comment on the Russian engine, although that was a part of the news, I don't know how many people know why we are using Russian engines. It actually goes back to the fact that it was part of the U.S. policy on nuclear reduction, that we bought the Russian engines to stop the Russians from using them against us. So we bought their inventory of motors, and it was and is a U.S. military program. It is the same motor that is in our Atlas V system. So the U.S. government, in an effort to reduce nuclear proliferation, has decided that the best way to do that is to buy the missiles that were going to be used to be ballistic missiles against us, intercontinental ballistic missiles, and we had an inventory of them. So then somebody said, well, we have all these motors, we might as well do something with them. Why not repurpose them and put them in our own rockets? So in some strange way, you find that that's, it's sometimes helpful to understand why that started. And it wasn't something that a bunch of companies decided to go out and buy Russian motors. It started because we began this process, and now they're continuing it. We are buying new motors from them, but the original design of the vehicles was for those motors that we are now buying more of, and it has helped us enormously cost-wise over the years. So I like to tell the fun story. We're using Russian motors, and originally our rocket industry here in the United States was done by Werner von Braun, who was one of the head Nazis of its day. So the world is a very interesting place sometimes.
Yeah, I think what we see from DARPA is that space is hard. It's always been hard. You can't build the kind of redundancies you get into systems like you can on the ground or even in the air, because you have to pay that weight penalty usually, and that you can't really afford to do that. So I think what we're trying to do from a social engineering and social engineering perspective is start to get industry invigorated so they start making those investments and want to go into space and get different assets up there rather than have it being a pure DoD or NASA government type perspective. And the more we can invigorate them and give them the reason to get into it, the less we have to pay. So we want to try to mature those technologies where they see the value and they see the commercialization where they can start to make money off of that. So I think that's where we're trying to change this. And we're seeing it. We're seeing SpaceX and these different companies pop up here in Nevada. We talked to Elon Musk doing all his SpaceX, and he's all in. He wants to put a lot of money in. He says we're going to Mars. So I think the turnaround is coming where we're starting to see more companies pop up, and then as these sort of as satellites start to shrink too, it makes it more accessible for small companies to get into to build those kinds of smaller launch vehicles. So I think that helps out, and hopefully we'll see in the future the reliability come up where we can start to get the systems that we need in space and get commercialization and get industry really interested.
Yeah, and I think just to be clear too, the NASA policy for why they were doing this was very clear and sometimes not really articulated very well, and that is that the idea was to cede low Earth orbit to commercial operators so that those resources that could then be put into the far more difficult challenges of interplanetary travel and building the next generation of satellites and being able to manage the more difficult things. So it was a practical decision that said, if I could put it in Navy terms, let's bring a contractor merchant marine ship in to move some of the cargo so we could put our resources in doing the next class of destroyer. And that's the decision that NASA is making. It's one the military has been doing for a long time. The Air Force does airlift using commercial airliners, and it's the same type of philosophy, maybe seen differently because it's new in space, but it's not really new in terms of U.S. government policy.
So, yeah, and Mark, I think that's a really good point, and that's a good distinction about the philosophy behind NASA moving toward commercial launch for low Earth orbit. And I think and maybe within the military and NAVSEA particularly, you see this as well. It has created political tension between the resources which would go to further develop commercial and the resources that are required for that beyond low Earth orbit exploration. And in fact, it's something that we want to try to proactively work as an organization that represents the whole of the profession to find that more common ground and move away from move away from that being a political either or type of mindset or argument to that which I think which was originally intended, which was really to let's do both and let's do both well and let's do both appropriately.
Yes.
Yeah. Okay, Tony, you get a second chance here.
Yeah, Philip, I'm trying out each microphone. I was struck by the comment about the partnership with NASA, sort of the dollar for dollar, which is probably just a calculation, but were certain laws or policies put in place by the government that made it easier for you to co-share investment with NASA on the things you want to do that maybe we don't have on the DoD side?
Yeah, Tony, there is, and that is around the intellectual property. And we do a vast amount of traditional FAR contracting work with the military, so we have a good sense of both. In the work that we've done with NASA, the default is that the company retains ownership to the IP and the design, with the government getting a use license for the ability to build or use it should I go out of business in my career. And that allows us to then contemplate making a serious investment in it, because that combined with the ability to use the technology for other purposes. So while I may do a NASA mission, I can also do a commercial satellite mission, or I can do a repair mission for the Europeans. Using that, those two combined together, where we retain ownership of the IP and we have dual use capability, are two things that then open up the door that says it's worth putting a certain amount of resources in doing. The payback for the government is that it then gets a significant reduction in investment. It also is milestone based. All my contracts with the NASA program that we mentioned are milestone based. The government only pays when I start performing, when I meet certain milestones, first flight, hypersonic flight, those types of things. So there's a protection for the government and for the taxpayers that allows these things to happen when they're shown. It's not a cost-plus contract. It's not a payment by number of hours per month contract. It's based on performance, which all three of those things put together drives at least in our sense, the commercial activities, the entrepreneurial activities. But with the government connection, the other part of it, the fourth part is, by having this formal relationship with the government, we get to have access to government resources when we need them. And that doesn't mean we get them for free, but it means that if we need to have an arc jet facility which tests heat, and there are two in the country, both owned by the government, we get access to that to do our testing. And that's hugely beneficial because we don't have to build that $500 million facility to go make that happen. So it's been a really nice work. But I think to answer your question, mainly the ability, if you don't need to own the technology and you are able to give that to the people developing it, they were more likely to put more money into it. Yeah, we provide the technology. Any of the technology the government co-invests in, it gets a copy of, essentially.
All right, so no one else is standing at the microphone, and we've had. I want to first want to thank Kyle and Mark for making it out here on a day like this, and for the presentations that both of them gave. I thought both were very informative, and thank you for first sticking around on a day like today, and for the excellent questions and the good interaction. I think we were scheduled to go until 5, but on a day like today, giving you 15 minutes back is probably not necessarily a bad thing. I know both Mark and Kyle, if you had questions that you wanted to ask, maybe individually, or just wanted to get a card to take with you in the event that something piqued your interest and you might want to follow up on either a technology that they've described or just a question in general, I'm sure they'll be happy to stick around to do that. So thank you very much for still being here, your attention, and your really engaged interaction with us. Thanks much.
Tom, Mark, and Kyle, thank you very much on this day for coming out. We really appreciate it, especially given the weather and everything. Two, the remarks were exceptional. We really enjoyed what you had to say. And three, if that beer option's still available, I'm willing to take it. And then, just so you know, for all of our panelists throughout the 2 days, we make a donation to the Wounded Warrior Foundation, so in your name. So.
Very good.
Yeah, thank you very much.
Thank you.
Thank you all.